is it gonna work? I don't know. It's working. Yeah. All right. So we're doing part 3 of the stats project right now. And with part 3, we are using the information from part 1. So I kept the same grouping, the same height and distance ran. That was the one that I chose. That was option 2. So for part 3, I'm keeping with option 2. Now this example only goes through 1, 2, 3, 4, 5 students, but you have to do it for all students, okay? So that's the thing for all this. You don't have to find the equation, it's given. Look at the Excel doc and it's highlighted in yellow. That's how I found it, right? You see it? Oh, so the best fit line is given to you. I'm not making you find the best fit line. Okay. So here's the thing, we had the best fit line, we had our scatter plot for part 2. Now in part 3, what we have to do is interpret the slope and y-intercept. Okay, so we need to start by, for the first part of this, we need to interpret this and interpret this. Okay, now here's the thing. I found this best fit line by plugging in all the data and using a regression tool to find the best fit line. There's actually a tool you can use to find that. So, but the thing about the best fit line is that it isn't always logical because the data points aren't always logical, right? This person's 70 inches tall and ran 10 miles. This person's 69 inches tall and ran 2 miles, right? So the trends with raw data that isn't contrived, isn't created, like in a math book, all that stuff is created. In a math book, they may have a best fit line that is a feasible option because they've designed the problem in that way. We are not dealing with that. We're dealing with actual data. You guys answered the surveys. This is your data, okay? So there's going to be situations where, like in this case, where we have to interpret, and we're going to interpret the y-intercept and the slope, okay? So this is how we're going to be doing each part of this. All right. Now I look at the y-intercept, that's over here, the y-intercept, and the y-intercept's negative 25. Negative 25. Remember, we're talking about height, which is going to be an x. Distance ran is going to be our y. So if I'm talking about the y-intercept being negative 25, that would mean that the distance run, since that's the y-axis, it would mean that if you're 0 inches tall if you're 0 inches tall, then you run negative 25 miles. How the heck? I mean, maybe we're talking about when, I don't even know what you're talking about. So in this case, our scenario does not make sense, or at least the best fit line, our y-intercept, does not have a reasonable interpretation. That's okay. I can put that. Okay. So let's see. Based on data, the y-intercept of negative 25 let's see, doesn't reflect the scenario. Okay, so based on the data, the y-intercept of negative 25 does not reflect the scenario. It's impossible to run negative 25 miles, unless if you're 0 inches tall, you run backwards 25 miles. That's craziness, okay? It's also, it doesn't make sense here because look, if I set up this graph, remember that we have height, right? And we have distance run, okay? So what we had here was, we had a lot of data points. I plugged in all those data points. It gave me a line of best fit, but the line of best fit has a y-intercept way down here. Right down here at negative 25. Now I have to look at my graph and think, what does this mean? This means when you're 2 inches tall, 1 inch tall, 0 inches tall, the furthest distance you run is negative 25 miles. That does not make sense. The scenario is relating height and distance run, but the line of best fit that is just going through the points, right? It's just based on where the points are, is showing that we have a y-intercept way down here, but that doesn't make sense with the scenario. And that is fine as an interpretation, okay? Because it's not a guarantee that the best fit line is gonna make sense for the data. The best fit line is just matching the raw data points. There's not a connection there where if it's the data points, then it has to make sense on the graph. The best fit line is just going through the data points. Okay, so there's like a definitely an interpretation where you say it doesn't make sense for the scenario. It doesn't reflect the scenario. Now the slope is going to reflect the scenario. Our slope is this: 0.5 over 1. You could have written this as 1 over 2. 0.5 is also 1/2. But I like putting it this way because that was the slope we were given. It was 0.5x over 1. So what this is saying is it goes up half for every 1 you go over to the right. Okay? It goes up a mile for every inch you go to the right. So remember that up is talking about distance. To the right is talking about height. The rise of the run is directly related to the rise, which is our y-axis, and the run, which is our x-axis. So if I'm looking at this, I see that my rise over the run is 0.5 over 1. So what is that saying? That's saying that their increase of 0.5 miles for every 1 inch taller. No problem, Zach. I'm recording this video. You can watch this first part later if you want. You see, so it's increase the distance, increase of a half a mile for every 1 inch taller. And that kind of makes sense. I guess when you get taller, you could run further. I mean, that kind of makes sense. If you're a little kid, you can't run a mile. If you're like 6, no, you can. I used to run when I was young. When I was way young. All right. So guys, let me know in the chat, on a scale from 1 to 5, how are you feeling about this? On a scale from 1 to 5, have you seen it? Are you okay with this first part? Interpreting. Yeah? Give me some more votes. Everybody vote. Everybody vote. Okay. Everybody vote. I need a few more votes. I'm not totally sure. I gotta know. I'm curious. I need to know what you think. I care about what you think. All right, thanks. Okay, so that was number 1. We just had to interpret. Okay, number 2 is use the correlation calculator. So we're finding the correlation coefficient. And we're going to use the correlation calculator. It's going to give us an R value. Okay, so we're going to use the correlation coefficient to find the R value. So I'll just show you real quick, and then I'll peek back to this screen. I think the recording will continue. But this is, I just want to point out, this is the correlation calculator. You've seen it. And we have to input our X values. It looks like I only kept 5 values. So I'm going to go add more. 1, 3, 4, 5. Okay. So as I'm doing this, I'm going to put in my X values. I'm going to use tab to go between the keys. So we have 70, 10. 60, 1.2. Wow. 1. Let's see, 60 and 1. 69 and 2. And 62.4, so specific, and 1.6. All right, then you're going to go ahead and calculate it. Looks like I need 1 fewer row. Yeah, that sometimes messes it up. Hey, I only have 5. Why are you saying 6? There we go. And there we go. We got our R value of 0.73. Okay. So if you're watching at home, you can just see this screen. Then you'll have to go to the assignment. It has the calculator. It's pretty self-explanatory. You plug in the X, you plug in the Y's, you push calculate, you get your correlation coefficient. Done. Oh man, part 3 is going to take no time at all. And then the last part of part 3 for the stats project here is looking at describe if the relationship is correlation or causation. Explain your answer. Okay. First off, one thing that you should know is there. All right, that's good. All right. So causation, let me remind everybody. I'll remind us of this. Causation is A definitely causes B. It was raining, so it caused the ground to be wet. Okay. Now, for real easy scenarios, causation is possible, but it's very rare. It's very rare that one thing perfectly causes another. Okay. It's rare that exactly the height causes how far you can run. Okay. Now, you might go through your whole academic career and never see a purely causal relationship, because causal relationships, causation, is rare. This is very rare, and you basically can only say something's causal if it's really basic, like dropping this pen. I could probably say very, very a lot of certainty that causation, it's going to fall. I drop the pen, it falls. Okay. But with anything that's complicated, anytime you're asking and doing surveys and asking between different things that maybe aren't related as well, it's never going to be causation. And that's really where number 3, you're describing why it's not causation. Correlation is when A is related to B. It may not cause B, but it's related, right? So if I said there's a high correlation between if you're tall and if you're good at basketball, that might be good. Or, well, not necessarily, because there's plenty of good shorter players or guards. How about the more you can bench press, the more you can curl? How about that? That's probably a pretty strong correlation. If you're strong in one way, you're probably strong with another muscle group if you're really working out. So the difference is correlation is relating. Relation. It's a relation. It's not causing. Yeah, you got it. You got it. Okay, so that's great. I'm glad I got to reiterate that. So if I'm talking about this number 3, I am going to look over and see what was my R value. This is not the R value for you, because I only did it for 5. You got to do it for all 20 something. But I'm going to say here that let's see. This is a moderately strong positive correlation. So I'll probably say the relationship is moderately strong positive. It's correlation. It's a correlation. Because of the R value and data that you could say contradicts a causal relationship. And that's a lot of writing, but that's what you have to write. Oh, not like this. Okay, so what I'm going to point out, though, when you're doing yours, you're basically saying why it's not causal. It's always going to be correlation. Everything's correlation. Causation's rare. So you're going to, for number 3, your argument, you could write it out. It's going to be a couple sentences, or like what I have here, about 25 words. The relationship is moderately strong positive. It's a correlation because of the R value and data that contradicts the causal relationship. Let's see if we can even find one here. Look at this guy. This guy here, let's see, 60, 70, 62. So let's see. Actually, everyone here, the taller you are, the more you can run. Okay. But let's say if we had another example here, this person's like 61 inches, and you probably have a data point like this, 61 inches, and you can run 7 miles. Well, that doesn't make sense, because I thought it was if you're taller, you can run further. So if I was down here and if this was a data point, I might even bring it up, right? So there's data that contradicts a causal relationship, like the kid who's 61 inches and can run, let's see, 7 miles, right? So if it was causal, then this kid would be running probably the similar amount as 60-inch tall and 61.2 inches tall, but this 61-inch tall kid can run 7 miles. So this is an example of why it's not a causal relationship, that if you're taller, you run further. And you could point out a contradiction like that makes it not causal. Okay. So why don't you guys get a screenshot? This is everything you need for number 3, and I will stop the video. Let's do that.